Everyone calls these giants diesel locomotives, but the truth is stranger. The engine inside never touches the wheels. Instead, it acts as nothing more than a rolling generator, unleashing electricity powerful enough to move 20,000 tons, but never through gears or a clutch. In fact, if you tried to hook up a normal transmission, it would melt in minutes. So how does a machine with no mechanical connection become the muscle behind the world's heaviest trains? The answer rewrites everything you expect about power and friction. Imagine trying to start a bicycle on a steep hill, but you are stuck in the highest gear. No matter how strong your legs are, the pedals barely budge. That is the same dilemma facing any internal combustion engine at standstill. A diesel engine, whether in a car or in a locomotive, produces almost no torque at 0 revolutions per minute. It needs to spin up before it can deliver any real pulling force. In cars, a clutch bridges that gap by slipping just enough to let the engine rev while the wheels start turning. The friction between clutch plates converts the difference in speed into heat, allowing you to ease forward until the engine and wheels are moving together. But now, scale that problem up to a freight train. A modern locomotive's diesel engine, like the GE VO12 V12, can deliver 4,400 horsepower, but only once it is spinning at hundreds of revolutions per minute. At 0 speed, it is as helpless as a cyclist in the wrong gear. The only way to get a train moving with a mechanical clutch would be to let it slip, just like in a car. But here, the numbers become brutal. Even a brief slip at full power, for example 10 seconds, would dump more than 30 million joules of energy into the clutch. That is enough to heat a ton of steel by nearly 100 degrees Celsius in moments. The clutch plates would glow red, warp, and eventually melt. No amount of extra surface area or cooling can keep up with the heat if you are starting a 10,000-ton load from rest, especially if you do it over and over in daily service. Early locomotive builders tried to solve this with bigger clutches and beefier gearboxes, but the result was always the same: overheating, warped parts, and breakdowns. The laws of physics do not scale kindly. The friction needed to start a heavy train cannot be managed by any practical mechanical system. That is why, for heavy rail, the old tricks of clutches and gears simply do not work. The problem is not just about size, it is about the fundamental limits of friction and heat. To move the world's heaviest vehicles, engineers had to find a new way to turn engine power into motion, one that does not rely on mechanical contact at all. A diesel locomotive starting a 10,000-ton train faces a brutal energy exchange. Imagine the engine delivering full power, over 3 million watts, while the wheels barely move. For the first 20 seconds, the train creeps forward, but the engine keeps pumping out energy at a relentless rate. In that short window, the engine produces about 65 million joules of work. Yet at such low speeds, the train's kinetic energy barely rises, reaching only about 23 million joules by the time it hits 5 miles per hour. That leaves more than 40 million joules with nowhere to go but straight into the clutch, if one existed. To put this in perspective, 40 million joules is enough to heat a full metric ton of steel by 80 degrees Celsius. If the clutch pack started at room temperature, it would be well on its way to a dull red glow, hot enough to weaken the metal, degrade friction linings, and trigger warping or outright failure. Stretch the slip time to a full minute, and the energy dumped into the clutch could top 200 million joules. The steel would rocket past 400 degrees Celsius, deep into the territory where mechanical strength collapses and surfaces begin to oxidize and deform. Even if engineers built a clutch with a dozen massive plates, each over 1 meter across, the contact area still would not be enough. The heat flux during a heavy start would be hundreds of kilowatts per square meter, far beyond what any forced air cooling system could handle. The only way to keep the clutch from melting would be to make it enormous, dozens of square meters of friction surface weighing several tons and still vulnerable to repeated starts. Packing that into a locomotive frame is physically impossible. No matter how much steel or cooling you add, the numbers do not work. The laws of thermodynamics draw a hard line. Mechanical friction cannot survive the demands of mainline freight. The only solution is to abandon friction entirely and look for a new medium to transmit power, one that does not turn every start into a thermal disaster. Inside a modern freight locomotive, the diesel engine is not there to turn wheels directly. Its job is to act as a steady, relentless power plant, a prime mover that delivers raw mechanical energy to the alternator bolted directly behind it. The GEVO 12, a 12-cylinder 4-stroke turbocharged diesel, is the heart of the GE Evolution series. It produces 4,400 horsepower or 3.28 megawatts at a typical operating speed of 900 revolutions per minute. That number is not chosen for drama. It is a sweet spot where the engine runs efficiently, burns fuel cleanly, and meets strict emission standards. What matters is not how fast the engine spins up or down, but how steadily it can deliver torque. At 900 revolutions per minute, the GE Evo 12 is putting out roughly 34,800 Newton-meters of torque to its output shaft. That is about 25,700 foot-pounds, a force strong enough to twist a steel beam like a licorice stick. In engineering terms, the relationship is simple. Power equals torque times angular speed. The diesel's job is to keep supplying that torque at a fixed speed, no matter what the train is doing. This is a fundamental difference from car engines or truck engines, which rev up and down with the throttle and respond directly to wheel speed. In a locomotive, the engine throttle does not control how fast the wheels turn. It controls how much power the alternator receives. As one veteran railroad engineer puts it, you are not driving the train with your foot, you are telling the engine how hard to push the generator. By running the diesel at a steady, optimized speed, engineers can extract maximum efficiency and reliability from the prime mover. The alternator in turn converts this mechanical power into electrical energy, ready to be routed wherever it is needed. The result is a system where the engine is free from a constant tug of war with changing loads and speeds. Instead, the engine focuses on one job: delivering a continuous stream of mechanical energy to the generator and letting the electrical system handle the rest. The alternator, spinning at the back of the diesel engine, produces three-phase alternating current, thousands of volts at frequencies tied directly to engine speed. But traction motors and their control electronics demand a different kind of power: high-voltage direct current. That is where the rectifier comes in. Mounted just downstream of the alternator, the rectifier is a bank of heavy-duty diodes arranged in a bridge. Its job is to take the raw, high-frequency alternating current and convert it to a steady stream of direct current, smoothing out the peaks and valleys into a powerful, continuous flow. This direct current does not just trickle through a single wire. It surges through thick copper bus bars, broad, rigid strips of metal designed to handle currents that can reach well over 1,000 amps under full load. Instead of a mechanical drive shaft, these bus bars form an electrical backbone, routing power from the heart of the locomotive to the trucks at each end. The advantage is flexibility. Copper can bend, twist, and snake through the locomotive's frame, making sharp turns and dropping down to the axles without concern for alignment or vibration. Where a steel shaft would need precise bearings and couplings, the electrical path can be split, branched, or rerouted at will. This system also makes it possible to distribute power evenly to all 6 axles, regardless of how the locomotive flexes over uneven track. At any moment, the direct current bus acts like a high-pressure main, ready to deliver instant energy wherever traction is needed. And because the alternator's output is rectified rather than fed directly to the wheels, the diesel engine is free to run at its most efficient speed, while the electrical system adapts to every change in demand. By conditioning the alternator's output into clean, controllable direct current, the rectifier and bus bars form the true shaft of the locomotive, one made not of spinning steel but of flowing electrons, ready to be divided and delivered to the traction motors that do the real work. Traction motors are the true muscle of a diesel-electric locomotive. Mounted directly on each axle, these electric machines do the heavy lifting, converting electrical energy from the bus bars into the twisting force that actually turns the wheels. In a modern 6-axle freight engine, each axle gets its own dedicated motor, nose suspended right above the gear it drives. The principle is straightforward. As soon as current flows into the windings, the motor produces torque, force that tries to rotate the shaft. Unlike an internal combustion engine, which struggles to deliver any torque at zero speed, an electric motor can push with nearly its full rated torque the instant it is powered. Torque in an electric motor is directly proportional to the amount of current delivered. More current means more twisting force, right from a dead stop. At the heart of each traction motor is a gap, just a few millimeters wide, between the stationary stator and the rotating rotor. Across this air gap, magnetic fields transmit force without any physical contact. There are no friction plates and no clutch linings to wear out. The only things that age are the bearings and the insulation, not surfaces grinding against each other. When the train starts moving, the motors can slip magnetically for as long as needed, limited only by how much heat the windings can safely absorb. Instead of mechanical friction, any excess energy becomes resistive heat in the copper coils, which is far easier to manage and cool than the concentrated heat of a slipping clutch. This magnetic coupling acts as an unbreakable clutch, a force link that never burns out no matter how many times the train starts or how heavy the load. At low speeds, the traction motors produce their maximum torque, giving the locomotive the pulling power it needs to get thousands of tons rolling. As speed increases, the control system dials back the current to protect the motors and match the growing resistance. But at the moment of starting, the full electrical muscle is available. This is the key advantage electric traction brings to railroading: the ability to deliver massive, controllable force at zero speed without the limits of mechanical friction or the risk of catastrophic overheating. In the era of direct current traction, managing the flow of electricity to the traction motors was as physical as it was electrical. Engineers relied on massive contactors, essentially industrial-grade switches, to rewire the traction circuit as the train accelerated. At low speeds, all the traction motors were wired in series, sharing the available voltage and maximizing current for the torque needed to get a heavy freight rolling. As speed increased, the control system reconfigured the wiring, shifting motors into parallel groups. This allowed higher voltage across each motor and reduced current, matching the changing needs of the train. Each transition was unmistakable. A deep metallic thud echoed through the cab as the contactors slammed open or closed. Veteran engineers could feel the lurch in the seat and hear the relay bank announce its work, a tactile reminder of the raw machinery at their fingertips. But with the arrival of alternating current traction and digital control, the entire process became invisible and much more precise. Instead of physically rerouting cables, modern locomotives use IGBT-based inverters to digitally sculpt the power delivered to each traction motor. The rectified direct current from the main alternator is chopped and modulated into variable frequency, three-phase alternating current, tailored for the exact speed and torque required. The inverter acts as an electronic gearbox, seamlessly adjusting both voltage and frequency on the fly. As the train accelerates, the inverter gradually increases the frequency of the current sent to the motors, matching the rising speed while keeping torque under control. This digital control brings a new kind of sensory feedback. Instead of the thud of contactors, engineers, and bystanders hear the distinctive singing of the inverters. The pitch rises and falls with the pulse width modulation frequency, a high synthetic whine layered over the diesel's growl. On a spectrogram, these tones trace smooth arcs upward as the train picks up speed, a visible fingerprint of the inverter's work. The change is not just about sound, it means smoother acceleration, finer traction control, and less wear on mechanical parts. The invisible gearbox is now a stream of electrons, orchestrated by software, turning the brute force of a 4,400 horsepower diesel into precisely managed motion. For the people in the cab, the old days of feeling every transition have given way to a world where the only clue is the song of the electronics. Long mountain grades push every braking system to its limits. On a fully loaded freight train, relying only on friction brakes, steel shoes pressed against steel wheels risks heat buildup, brake fade, and even catastrophic failure. The energy of a descending 20,000-ton train has to go somewhere, and traditional brakes simply cannot absorb that much heat for long stretches. That is where the true versatility of electric traction motors comes into play. With the flip of a control, the same motors that push the train uphill switch roles and become generators, harnessing the momentum of the train to produce electricity instead of consuming it. This process creates a powerful magnetic drag on the wheels, slowing the train without touching the brake shoes. The sensation is unmistakable. One engineer described it as holding back a river with a magnet. The force is smooth, continuous, and does not rely on friction, so there is no risk of brake linings overheating or wearing out. This generator mode does not just protect the equipment, it gives crews precise control over massive loads on the steepest grades. Every watt of energy pulled from the train's motion is turned into electricity, setting up the next challenge: how to safely handle all that power. The energy pulled from a speeding freight train does not just vanish. On a diesel-electric locomotive, that energy goes up to the roof. As the traction motors shift into generator mode during dynamic braking, they pour megawatts of electricity into a bank of resistor grids mounted above the engine compartment. These grids are built from heavy steel bars, and they have one job: turning raw electrical power into heat. As the train descends a grade, the wheels spin the motors, which feed current into the rooftop grids. There, the energy is dumped as heat, often enough to rival a small industrial furnace. To keep the system from overheating, massive fans kick in, blasting air through the grids and out the louvers. Their high-pitched roar is unmistakable, sometimes louder than the diesel itself. In full dynamic braking, a locomotive can dissipate several megawatts through these grids, making the roof function like a giant toaster, glowing with invisible heat and announcing its presence with the steady howl of forced air. Every hour, thousands of locomotives move nearly 40% of United States freight using electricity as their invisible muscle. As global supply chains demand cleaner, more efficient transport, the hybrid logic behind these giants is more relevant than ever. Solving friction with magnetism is not just engineering, it is the future of heavy industry. Next time you hear that rising electric hum, remember, it is the sound of power reimagined. Share your thoughts below.